Hello, class. Continuation of lectures 10.1, where we're doing confidence levels with two means, two samples. And so here is our example that we're going to walk through. Last lecture, we talked about a bunch of definitions to get us to this point. And so again, this is something that works quite well in the pharmaceutical industry here. So say like you developed a new drug, again, we talked about this high blood pressure. And to test the drug, a sample of 15 patients is recruited to take the drug. And so that says that their systolic blood pressures are reduced by an average, which is the mean, 28.3, and a standard deviation of 12. In addition, another sample of 20 patients takes a drug that the blood pressure in this group are reduced by 17.1, and their standard deviation was 9. Assume the blood pressure reductions are approximate at normal distribution, right? Because it's not greater than 30, so we have to make that assumption. Find the 95% confidence interval for the difference between the population means for the new drug and the old drug. Okay, so let's take a look at this. And I'm going to walk through this on the whiteboard with all our calculations here. Okay, so well, what do we know here? Well, we know here's the new drug, right? So here's the new drug. And we're going to call that X1 bar for our calculation. And so that mean is 28.3. We had an N of 14, number of people, and our standard deviation S1 was 12. Okay, so the old drug. So the old drug is set up where the X2, we'll call that, was 17.1. And that standard deviation, whoops, I have N first, so let's keep this consistent. So we'll call that N2. That was 20. Oh, I'm sorry. Let me fix this here. I'm reading the numbers wrong. N1 was 15. I was looking at the degrees of freedom, which we'll talk about shortly. And the standard deviation here was 9. So to refresh your memory, this point estimator will be X2 bar minus X1 bar. And then our MO, margin of error, again, is the T, and they use the alpha divided by 2. In this case, we're at 95%. And then it's the square root. So this is multiplied by S1 squared over N1 plus S2 squared over N2. So that's what we need to calculate. So how do you do that? Well, we're doing a 95% confidence interval. And so what is our degrees of freedom? You remember that term? Well, when you do this by hand, the degrees of freedom is calculated by the idea, and I need another either. You take the smallest sample size and subtract 1. So in this case, our smallest sample size is 15. So our degrees of freedom would be N1 minus 1, which would be 15 minus 1, which would be 14. So you could look this up on a table. Let me pull the table up. Okay, can we get to the table now? Okay, so here's our table, right? So the idea is that we're doing a 95% confidence level. So for the two tails, it'd be 0.05. And we go down to 14, and you can see our t-value is 2.145. So it'd be right here. So we go back to our whiteboard. Let me write that in there. So then our T alpha over 2 is 2.145. Okay, so what's next? So what's next now is we want to calculate the mole. And so that would be 2.145 times this crazy thing, right? So, but you just have to plug them in. It's not absolutely horrible, right? And so if we plug those in, we would get, let's see, so that would be 12 squared divided by 15 plus 9 squared divided by 20. And if you did that, you would see that that would be 2.145, and this would be 3.6946. So if you multiply those two together, you would get 7.925. So this is our mole. So our mole, I'm going to stick it down here, is 7.925. Okay, so what's next? Well, we need to find our point estimator here. So let me get rid of this. So the point estimator hopefully is the easiest one. So that would be x1 minus x2, x1 bar minus x2 bar, excuse me. And so that would be 28.3 minus 17.1. So if you did that calculation, this would be 11.2. And so it's good that the new drug is quite a bit better, it looks like, than the old drug by 11.2. And so what do we do now? Well, what's the low end, right? The low end would be 11.2 minus the mole, which is 7.925. And so if you did that, and we'll just round, you would get 3.3. And the high end, all right, what did we call that? Upper end and lower end, I think maybe. But the high end would be 11.2 plus 7.925. And so when you add those together, we'll round to one decimal, you get 19.1. So our range for our point estimator is 3.3, be less than x1 minus x2 is less than 19.1. So that's how you do it by hand. A little tedious, but hopefully not horrible if you keep all the numbers straight. I put it on pause there for a little bit. I was doing the spreadsheet calculation to show you, and I did realize that I used different terms in chapter 8. So I want to be consistent. So instead of this lower end and upper end, we use bounds. So this would be the lower bound, LB we called it, and the upper bound, UB. And that's how you do it by hand. And you'll see that you do it in the homework. There will be a couple of these that you're going to do by hand. And the reason why there is a difference, and that doing it by hand or using technology, is this idea of degrees of freedom. So what do we mean by degrees of freedom? Well, when you do it by hand in the Welch's method, you use the simple calculation of picking, again, the smallest of the two sample sizes and subtracting 1. If you do it with technology, let me show you what the crazy formula looks like. So the crazy formula, well, here was the calculation we just did by hand. Here is the crazy formula for degrees of freedom using technology. And it's a real pain to do by hand using this degrees of freedom. And what will end up happening is the degrees of freedom will end up being a fractional number instead of a nice whole number. And so guess what? The table isn't that useful as well. So you have a couple options. Option one is to use your calculator. And this is the two sample interval command. And so this is this idea of plugging in all these values, and you'll hit polled equals no in the two sample interval. And you see that you end up with 3.59 for the lower bound and 18.809 for the upper bound. And you could see that the degrees of freedom, instead of being 14, ends up being 25.022 in the calculation using the more sophisticated and more accurate formula. So is 3.3 that much different than 3.6? And what was our other one here? Let's see. Whoops, again. Keep hitting the wrong button here. I get back to the whiteboard. So, and then we had 19.1 instead of 18.8. Not too bad, right? But if you're looking for a more accurate calculation, you can use your calculator. So what I did is generated a spreadsheet for everybody that you would be able to use as well. And let me show you what that spreadsheet looks like. So here is the spreadsheet. And so what I put in here are the S1, S2, N1s, and then the two X1s, right? So these are the numbers. So here is the calculation, and here's the crazy degree of freedom. And I uploaded this spreadsheet to Canvas, so you have it. So all you need to do is to put the right numbers in here, and the formulas are already set up for you. Because you can see here is the t-score, and I programmed that crazy formula into the cell here. Very complicated. Let me rephrase that. It's not that complicated if you know what you're doing. It's a little bit complicated if you've never done a complicated formula before. So I did it for you. And so here I went to the inverse, and this will give you the t-score. Sorry for the pause there. I had to add one more function here, is that you have to plug in the alpha. And so this is 95%. Just plug in the 95. If it was 99%, you plug in 95 because you need that to calculate the t-score. And so with that, this is used to calculate the t-score. Here's our degrees of freedom with that crazy equation. And then here's our MO, margin of error. Here's our X1 minus X2. And here we have the upper bound and lower bound. So this ends this recorded lecture. I'm going to do one more where I'm going to actually do a homework assignment from the ALEKS program and show you how you could use this spreadsheet and to do those calculations if you don't want to use your calculator.